All right, hello everyone. We're in section 7.4. 7.4 is titled Separable Differential Equations. I talked a while back about the fact that we were going to kind of dabble into some differential equations. We've done the most basic type of differential equation so far. And then we've learned a little bit about slope fields also. So we're going to actually go back in time a little bit today, a little Algebra 2 review also. So this is what's called a separable differential equation. Just as a quick review, everything we've had so far has just had x's in them, right? So, which meant we just found the antiderivative. Then we did some slope field stuff where it had x's and y's, and we talked about not actually solving those, but about just drawing a picture of them. So the main difference between a regular differential equation that we've dealt with and a separable differential equation is the fact that you typically, but not always, have x's and y's in them. So notice x's, and y's, right? So we will at least have y's in them. There doesn't always have to be x's in them, believe it or not. But if there's just x's in them with no y's, then it's just an antiderivative. But this most common type has both x's and y's, but might just have y's. It's called separable because what we're actually going to do is separate the y's from the x's and then solve two different antiderivatives. So pretty straightforward process, not too hard. The reason we're doing this right now is because it falls into place with some Algebra 2 stuff that we did, actually, some exponential growth, things like that. So here's how this works. Just going to give you a couple examples. We actually separate the y's from the x's. So notice the dy and the dx actually got separated. You can kind of separate them because they're just the operators. So we want the y's with the y's and the x's with the x's. So I divided, real quickly, just divided both sides by 1 plus y squared. Basically, canceled out that. And I wind up with dy over 1 plus y squared equals 2x e to the x squared dx. We have two different antiderivatives to find now, one with y's and one with x's. So what you see me here doing is just putting an integral sign on both of them so we know what we're doing. So we're solving because we're trying to find y. Remember, again, this solving a separable differential equation. Any differential equation is finding y. So I have two different antiderivatives to do. Over here, what you see me doing is a little u substitution on the x side. So one of the things that's going to happen in these separable differential equations, you could wind up with any type of antiderivative. Use substitution, integration by parts, one steps, power rules, whatever. So I did a little u sub over here on the right. Didn't really do anything on the left yet. I will here in just a second. Actually, I left that alone right there. So what you see here is that 2x canceled with that 2x, and I wound up with e to the u du. So now I'm going to integrate both sides. The left side is a tangent inverse. Hopefully you recognize that as a one-step antiderivative. And then we have e to the u plus c. There's technically a plus c on this side also. But what I do is just take that plus c, bring it over to here, and add it to that c, and it's just another constant. It could be anything. It's not really zero because they're not the same c. But we just put the plus c on one side. It's also really important that you put that plus c right now. A lot of people tend to put the plus c at the end, but the plus c is really super important, especially if we have an initial condition trying to find it, because what's going to happen is that c is going to wind up inside of a function. Watch, because now I need to solve for y. So solving for y. Sorry, I went back and made that substitution first. Tangent inverse y equals e to the x squared plus c. And then I solve for y, I take the tangent of both sides. So I get tangent of e to the x squared plus c. Notice that c is inside the tangent. It's inside the tangent. So if I did have an initial condition in this problem, that's how I would have to solve it to find c. Okay. So part of tonight's homework is just solving a handful of these. They're pretty straightforward, good practice in integration also. But the main reason we're showing you this right now is because of some formulas that we learned in Algebra 2, actually, that come from separable differential equations. So I'm going to go through these pretty quickly. They're going to be formulas that you've already seen. So remember bacteria growth, population growth, exponential growth, growth and decay, actually, comes from the fact that bacteria grows at a rate that's directly proportional to the number of bacteria. So we're just going to find this formula. Okay, this is a separable differential equation, so I'll show you one more here, and we're going to wind up with a formula you've seen before, actually. So notice rate of change. The bacteria grows at a rate directly proportional, okay, to the amount of bacteria, which we're calling Y in this particular case. Okay, that's where all of our bacteria growth or exponential growth equations come from, is this fact. The more there is, the faster it grows. The less there is, the slower it grows. All right, so I'm going to solve this differential equation. K is a constant, so K can actually go anywhere. We typically leave it with the x's. In this case, it's not x's, it's t's for time. We typically leave it with that because remember, we're going to have to solve for y. So if I left the K with a y, I'm going to have to get rid of it and put it on the other side anyway. So it's just a constant. It's just going to float around. So the y's go with the y's. The t's go with the t's. There are no t's in this case. So this is an example, like I mentioned before, where you might not get x's. So you just get dy over y equals k dt. Natural log of y equals kt plus some constant c. Now we're going to do some little logarithm tricks here. First of all, we're going to solve it. So I'm going to exponentiate both sides. E to the ln y is equal to y, so I get e to the kt plus c. We're going to do some little exponent tricks here to get an equation that we're familiar with. What I did was I broke up this e to the kt plus c into e to the kt times e to the c. I would add those exponents, right? So that's e to the kt plus c. The reason I did that is to try to just make it look a little bit better. So this e to the c is just a constant, just some number. So I just called it d. I could have called it c again. You can call it whatever you want. I tend not to like to call it c again because it implies it's the same c it was at the beginning, but it's not. So I just called it a constant. So d e to the kt. And then if we start at time 0, so I put a 0 in for t, you get y equals d times e to the 0, or which is 1, you just get y equals d. So when time equals 0, y is d, so that's what we call the initial amount. So I just kind of rephrase this here and called it y sub 0 for the initial amount. So you might recognize this formula as this formula here. You, I think, probably called it back in algebra 2, y equals p e to the rt. It's the same thing, right? That's sometimes we call it the PERT formula. P is the initial. This was like for continuous compounding growth in money. P is the principal and R is the rate. It's the same formula. Okay. So we could solve some problems. They're just algebra 2 problems, really. So once we get into the problems, there's no calculus involved, just so you know. The calculus comes from the formula. Which is why it's introduced here. But once we have a formula, then that's all we need, right? So we start with this formula. The number of bacteria increases from 600 to 1,800 in 2 hours. So I'm going to call my initial 600, and at time 2, 1,800. So what I'm going to do is start with y equals the 600. That's my initial, e to the kt. What I need to do is find k, so I have my equation, but I now have a point of reference. When time equals 2, there's 1,800. So we're going to go 1,800 equals 600 e to the 2k. 3 equals e to the 2k. These are all meant to be done without the calculator, by the way. Sometimes the numbers come out not great, but I'm going to do this without the calculator so you can see it. You take the natural log of both sides. So I get the natural log of 3 equals e, sorry about that, natural log of e to the 2k, which is just 2k. So k is the 1/2 times the natural log of 3. So when I go back to my equation, I get 600 for my initial e. My k is 1/2 natural log of 3. But watch this. I'm going to do a little trick here. I'm going to raise that power up there just to make it a little bit easier to deal with. So watch this. I'm going to come up here. So I'm going to get ln of 3 to the 1/2 times my t. Okay. But I can also raise that t up there. So I wind up with y equals 600. So I'm going to just bring this t up there actually also. So e to the natural log of 3 to the t over 2. And remember that e to the natural log of anything is that anything. So I wind up with 600 times 3 to the t over 2. So now I have an equation, so I can answer any questions. You go back to the question, how many bacteria would be in 5.5 hours? I'm not going to do this at this point. I would just stick 5.5 in for T. At that point, I maybe need a calculator. Normally at this point, if it's a non-calculator problem, we'd make that number really nice. So we would say, how much bacteria is there after 6 hours? So 6 divided by 2 is 3. 3 to the third is 27. You can do that without a calculator. If you feel like the numbers are bad and you need a calculator, go ahead and use a calculator. And then there's one other little application of this, and it's called Newton's law of cooling. It's the same basic idea. An object cools or heats at a rate directly proportional to the difference between its temperature and the temperature of the surrounding medium. What this means is this: if you put something hot into a freezer or something cold into an oven, let's say you put something cold into an oven, right? So let's say the oven is at 400 degrees. And let's say you're starting at something that comes out of the freezer at 32 degrees or something like that. If you throw this in the oven, it's going to increase really fast at the beginning. But then when the difference between the temperature of the object and it's just that 400 degrees gets closer, then it's going to slow down, right? It's going to kind of do something like that. So that's kind of the general idea of Newton's law of cooling. We can get a formula for this the same way we just did the other ones. So I'm going to do it with a specific problem and then I'll generalize it. So we got a certain object that cools from 125 degrees to 100 degrees in half an hour when surrounded by air at 75 degrees. Find its temperature after another 30 minutes. So remember, Newton's law says the rate of change, that's the dy dt, is directly proportional to the difference between the temperature and the surrounding median. So y is the temperature, 75 is the surrounding median. So I have another separable differential equation that I can go ahead and solve. We're going to ultimately get to the formula. By the way, sorry, I should have said this back in these problems. Once you have this formula, you don't ever have to do that again. And we know that formula. So it's not like you have to go through that process every time. Same thing here. I'm going to come up. We could go through this process every time, but I'm going to give you a formula at the end to help you memorize it. So it's a separable differential equation. The y's go with the y's and the t's go with the t's. So we get dy over y minus 75 equals k dt. Integrate both sides. I get the natural log of y minus 75 equals kt plus c. I'm just going to solve it for y, remember? So I'm exponentiating both sides. E to the natural log of y minus 75, e to the kt plus c. So you get y minus 75 equals e to the kt plus c. Broke it up just like I did last problem. Y minus 75 equals e to the kt times e to the c. And then remember, I just called this e to the c d, and then I added 75. So this is my general equation, right? Y equals d e to the kt plus 75. But now I need to deal with the initial point, right? So we started this thing, at around 75 degrees. The air, it went from 125 to 100 in half an hour. So the initial temperature is 125, right? So what that means is when I put in T equals 0, I'm supposed to get out 75. So I go 75. Sorry, I kind of jumped ahead here. 75. Let me try that again. The initial temperature is 125. Sorry, I know what I'm doing. Let me try that again. Sorry, the initial temperature is 125 equals my D, and then e to the kt is going to be e to the 0 because times 0, which is 1, plus 75. So we get D equals 50, which is what you see me with my original equation there. If you generalize this, here's what happens. You get y equals the difference. So this is the difference in the temperatures, okay, times e to the kt plus the surrounding temperature. So 50 is the difference between the 125 and the 75 at the beginning. And then the surrounding temperature is the 75. So you don't have to go through this process every time. I'm going to stop right now. I think you guys can figure all the rest out, right? We have an equation. We have other information. So it went from 125 to 100 in half an hour. So what I would do now is go 100 equals 50 e to the 1/2 k plus 75. I'm going to not do the algebra for it. I'm going to stop here because we're just going to solve for k. with that initial condition. And once I have K, I can answer any questions, just algebra equations at this point. So that's it for separable differential equations. You're going to get a little practice at the separable differential equations. And then remember the problems that look like growth, exponential decay, growth, this sort of problems. You do not need to go through these formulas every time. Those formulas are something you know and you can just go ahead and use. You don't have to generate them every time.